How fast an actuator operates depends on the rate at which it is filled with fluid. In many hydraulic applications, it is necessary to regulate this rate. That is, to control the velocity of actuators. One way to accomplish this would be to change the output of the pump. But this would affect all parts of the system, not just a specific actuator. A common way to regulate flow in a system is to use a flow control valve. As we saw in an earlier lesson, these valves control the rate at which fluid flows into or out of an actuator. In this lesson, we'll take a close look at how flow control valves work and how they are used to control the operation of hydraulic actuators. The rate at which fluid passes through a flow control valve depends mainly on three things: the size of the orifice in the valve, the pressure differential across the valve orifice, and the viscosity of the fluid moving through the valve orifice. The orifice is the restriction in the cross-sectional area in the flow control valve. The larger the orifice, the more fluid can flow through it. In some flow control valves, the size of the orifice is fixed and cannot be changed. However, many systems require that the size of the orifice be adjustable. Gate valves, globe valves, and needle valves are all examples of variable orifices. A gate valve permits flow straight through its center. The size of the orifice is determined by the position of the gate. Normally, gate valves are used either to shut off fluid flow completely or to open the valve up all the way. When more than just on-off service is necessary, globe valves and needle valves are used. Of these two, needle valves provide the most precise and controlled adjustment of flow rate. As a flow control valve is opened, the flow rate through it increases. This, in turn, increases the flow rate into an actuator and increases its velocity. Closing down the orifice reduces the flow rate and reduces the actuator's velocity. Flow rate is also affected by the difference in pressure between high pressure on the upstream side of the valve's orifice and low pressure on the downstream side. The greater the difference in pressure, the greater the flow rate. That means that if the pressure on the downstream side of an orifice drops, for example, if the load becomes less, while the pressure on the upstream side remains constant, then the flow rate will increase and the actuator will speed up. And if we keep the upstream pressure constant while we raise the pressure created by the load, the actuator will slow down. Changes upstream of an orifice can also affect flow rate. For example, if pressure ahead of an orifice increases while pressure downstream remains the same, flow rate will increase and the actuator will speed up. Decreasing the pressure ahead of an orifice while pressure downstream of the orifice remains the same will cause the flow rate to decrease and the actuator to slow down. In most hydraulic systems, steady actuator velocity is required, but very often there are frequent fluctuations in the system pressure. That means we need some way to compensate for these pressure changes. The device that does this is the pressure compensated flow control valve. This valve is designed to maintain a constant pressure differential across the valve orifice. There are two types, restrictor and bypass. The restrictor type is the most commonly used in industrial hydraulic systems. It has a valve body with an inlet port and an outlet port, a needle valve, a spring-biased compensator spool, and two pilot passages. One pilot passage compensates for fluctuations in upstream pressure, and the other compensates for fluctuations in downstream pressure. The pilot passage that compensates for upstream fluctuations directs fluid pressure to one end of the compensator spool. As the spool moves, it blocks off part of the flow until pilot pressure equals the tension pressure of the spring. For instance, suppose the valve has a 100 psi spring and inlet pressure is 500 psi. In operation, pilot pressure will push the spool over until pressure downstream of the restriction created by the spool is reduced to 100 psi, the tension pressure of the spring. The remaining 400 psi is converted into heat and carried away by the fluid. If upstream pressure rises, the spool continues to shift. For example, if inlet pressure rises to 600 psi, the spool will shift a little more. The smaller restriction will lower pressure downstream of the restriction to 100 psi, and the remaining 500 psi will be carried away as heat. As long as there is no load, the pressure just downstream of the restriction will equal the pressure of the spring. The difference between this pressure and the inlet pressure is always converted into heat. However, there usually is a load at an actuator when the system is operating. Changes in the workload create pressure fluctuations downstream of the needle and also affect the flow rate. These fluctuations are compensated for by the other pilot passage. This passage connects the spring side of the spool to fluid pressure downstream of the needle. As a result, pressure created by the resistance of the load downstream of the valve helps the spring push the spool back. To see this clearly, let's look at a circuit. In this system, the relief valve setting is 400 psi and the workload pressure is 200 psi. The spring biasing the compensator spool has a tension pressure of 100 psi. When the system is operating, pressure upstream of the restriction is limited to 400 psi, the setting on the relief valve. Pilot pressure tries to push the compensator spool over until pressure past the restriction equals the spring tension pressure, 100 psi. However, the compensator spool cannot move that far because 200 psi from the load pushes the spool back. The restriction is widened until this pressure here, the pressure between the restriction and the needle, is 300 psi. This pressure equals the sum of the load pressure and the tension pressure of the spring. The difference between this pressure, 300 psi, and the pressure created by the load, 200 psi, determines the flow rate through the orifice and affects the speed of the actuator. If the load creates more resistance, say it creates a pressure of 300 psi, then the compensator spool is moved back even farther. This widens the restriction, so the pressure between the restriction and the needle rises to 400 psi. Just as before, the difference between 400 psi and 300 psi, or 100 psi, determines a flow rate that controls the speed of the actuator. Notice that in this example there is no pressure differential across the restriction, and no excess heat is being generated. That's because the pressure from the load has pushed the compensator spool all the way back. Since additional increases in the load will not be able to push the compensator spool back any farther, the valve will be unable to compensate for any more changes in pressure from the load. When using this kind of pressure-compensated flow control valve, the system's relief valve setting must be at least as high as the workload pressure and the spring pressure. Otherwise, the valve will not be able to compensate for changes in pressure. Now, suppose pressure changes both upstream and downstream at the same time. For example, let's say the relief valve is reset for 700 psi and the workload increases to 400 psi. As before, the pressure between the restriction and the needle will equal the sum of the load pressure and the spring pressure. So it would be 400 psi plus 100 psi, or 500 psi. The difference between the pressure at the workload and the pressure ahead of the needle does not change, so flow rate and the velocity of the actuator remain the same. At the restriction, excess heat is being generated because inlet pressure has risen. Just as before, the difference between inlet pressure and the pressure between the restriction and the needle becomes heat. In this case, it would be 700 psi less 500 psi, or 200 psi, which will be converted into heat. Now let's look at the other type of pressure-compensated flow control valve, the bypass type. Like the restrictor type, it has a valve body, an inlet and outlet port, a needle valve orifice, a compensator spool, and a spring to bias the spool. However, instead of two pilot passages to compensate for changing pressures, it has one pilot passage and a port to tank. The port to tank compensates for changes in pressure upstream of the valve, while the pilot passage compensates for changes in pressure downstream of the valve. In this type valve, the compensator spool blocks flow out the tank port until pressure rises high enough to overcome the combined pressures of the spring and the pilot pressure downstream of the needle valve orifice. When that happens, the spool moves and fluid bypasses the orifice, dumping directly to tank. Let's look at a circuit to see how this type of flow control valve works. In this system, the relief valve is set to open at 500 psi. The workload pressure is 200 psi, and the spring biasing the compensator spool has a tension pressure of 100 psi. Because the combined pressure of the bias spring, 100 psi, and the workload, 200 psi, pushes down on the compensator spool, pressure upstream of the needle orifice must rise to 300 psi before the spool will move. When that happens, fluid dumps to tank, limiting pressure to 300 psi. Pressure downstream of the needle orifice is the load pressure, 200 psi. The 100 psi differential between pressure upstream and downstream of the needle valve orifice, as well as the size of the orifice, determines the flow rate through the orifice. If workload pressure drops to 100 psi, for example, then the combined pressure of the bias spring and the workload drops to just 200 psi. The spool shifts at 200 psi, sending fluid to tank. But the pressure differential across the needle valve orifice is still 100 psi, so the flow remains the same. If workload pressure increases to 300 psi, for example, then the combined pressure of the bias spring and workload is 400 psi. The spool shifts at 400 psi, sending some fluid to tank. But the pressure differential across the orifice is still 100 psi, so the flow remains the same. If system pressure increases, say the relief valve is reset to 600 psi, the compensator spool will still shift at 400 psi, the combined pressure of the workload and the spring. Pressure at the valve inlet and pressure just upstream of the needle valve orifice will still be at 400 psi. Flow rate through the orifice will remain the same, while flow to tank will increase. So far, we've discussed two of the three main factors that affect flow: orifice size and the pressure differential across the orifice. The third is fluid viscosity. We learned in an earlier lesson that viscosity varies with changes in temperature. As fluid gets hotter, its viscosity decreases, and more of it flows through the orifice. As fluid gets cooler, its viscosity increases, and less of it flows through the orifice. To handle the effects of temperature variations on fluid viscosity, a device called a temperature compensator can be incorporated into the pressure-compensated flow control valve. In some valves, the temperature compensator is an aluminum or bimetallic rod connected to the movable part of the variable orifice. Aluminum expands more with changes in temperature than steel does. As the fluid gets hot, the rod lengthens, reducing the size of the flow path past the orifice. The hot fluid flows more easily, so the flow rate through the restricted orifice is the same as the flow rate of a colder fluid through a larger orifice. The opposite is true if the fluid is cooler than normal. The rod contracts, increasing the orifice size. Because the cold fluid has a higher viscosity and does not flow as easily, the same amount of fluid passes through the orifice. More commonly, flow control valves use a sharp edge orifice for temperature compensation. Within limits, this type of orifice ignores differences in viscosity. Let's say we have two tanks of the same size with identical sharp edge orifices in the bottom. Hot oil is in one, cold oil is in the other. When the stoppers are pulled from the orifices, the cold oil will flow out just as fast as the hot oil. Precision-made sharp edge orifices provide very accurate control of flow rate, despite changes in fluid viscosity. One problem when using pressure-compensated flow control valves in a circuit is that they sometimes cause an actuator to lunge or move suddenly when the valve first begins operating. This occurs because the valve permits a brief surge of higher than normal pressure to pass before the compensator spool moves into position. To prevent lunge, a screw adjustment is added to the valve to keep the spool from returning all the way to the end when the valve is not operating. Adjustments of the lunge control are made during normal operation by turning the screw in until it makes contact with the end of the spool, then backing it off slightly. When this is done, the spool remains closer to the position it will occupy during normal operation, so the rise in pressure before compensation occurs is smaller. However, because lunge controls limit the pressure compensation which the valve can produce, lunge control should be used only where load pressure remains relatively constant. One other common method of controlling the speed of actuators is to bleed off a portion of the flow before it gets to the actuator. This can be done by using a flow control valve to bypass a portion of the system's total flow back to tank. For example, if a pump develops a flow rate of 100 GPM, but the actuator requires only 90 GPM, we could use a large flow control valve capable of reducing the 100 GPM flow to 90 GPM. Or we can install a smaller, less expensive flow control valve to handle just 10 GPM in what is known as a bleed-off circuit. This smaller valve controls the flow to tank rather than flow to an actuator. A disadvantage of a bleed-off circuit is that it does not offer precise flow regulation to an actuator. Since the downstream side of the valve ports to tank rather than to the actuator, the valve cannot compensate for changes in load pressure at the actuator. In all the flow control circuits we've seen so far, the flow control valve has been on the inlet side of the actuator. These are called meter-in circuits. This meter-in technique works well as long as a load is being moved in one direction and there is no need to control the velocity of the return stroke. A meter-out circuit can be used to provide that control. In a meter-out circuit, the valve operates the same way it does in a meter-in circuit, but the valve itself is placed on the outlet side of the actuator. As a result, the valve controls the flow out of the actuator rather than into the actuator. In this lesson, we have shown how flow control valves are used to vary the velocity of actuators by controlling orifice size and by adapting to changes in fluid pressure and temperature. In the next lesson, we'll look at directional control valves.